Okay, back with magnetostatics. Okay, let's look at the Lorentz force law, right? The Lorentz force law. All right, this says that the force is equal to Q times my velocity cross B. All right, let's do kind of one of the simplest problems that one can do. Imagine the following example. Imagine that V equals V I hat. So it's some non-zero number times the direction I hat, and B is some uniform magnetic field. How would I generate that? You can use a Helmholtz coil in order to do that. A not terrible approximation would be to have a magnet with its north pole and a magnet with its south pole here, and here you're going to get fairly uniform magnetic field lines between these poles. It won't be perfect. If you really want it perfect, Helmholtz. All right, so what's the force going to be? Well, the force is equal to Q V I hat cross B J hat. So I do the work. And this tells me I get Q, V, B, and then I get I hat cross K hat, I hat cross J hat, which ultimately is K hat. All right, so let's think about what's going on here. So I have a magnetic field which is pointing into the board, right? So I'm drawing my magnetic field with X's, right? So what it's like, remember, into the board, we draw with an X. It's like if we have an arrow, right? So here's the tip, and then we have the feathers, which are X's. So if you're looking at the back end of your arrow, you see X's. Where if you're looking at the front end of your arrow, you see a point, right? So of course, X's means it's a uniform field. Well, a nice grid of X's means it's a uniform magnetic field, right? So, and if they're pointing into the board, that means that J is in. So if J is in, so if we start with I, or the X direction here, X, J, K. So, right, X, J, K. Then that's going to be Z, right? So X, right? So, right, you guys know this one, right? I put this one in the direction of the J hat, right? So I have X, J, and then up will be my Z direction. All right, so if it starts moving in the I hat direction, my charge here is moving in this direction, okay? And it feels a force which is moving in the K direction. So it ultimately feels a force here. So this is my speed, and my force is perpendicular to my speed. Okay? So that what's that going to do? It's going to cause this thing to start to curl, right? It's going to start to bend. Okay. And if I look at it right here at some other point, all right, its speed here is going to be V. Now, I can break that up into its X and its K components, right? But rather than do that, let's just redefine my axes so that my axes now point along the X direction here, this new X direction, X prime, and that's my z prime. Well, if I know, then I know my velocity, right, is going to be, I can write my velocity to be v, you don't know what it is, so we'll call it v1, I hat, right, in the new prime coordinates, right? So where the j stays the same, right? So I have x, y, right, y, z. So the x hat has been redefined, so it aligns along the velocity. The j has stayed put, but now we have to redefine our z. So if we go through the same process again, b equals v 1 I hat prime, right? And then b is equal to b j hat. So then when I do the cross product, well, now I have I hat prime cross j hat. So it gives me k hat prime. So that tells me, well, wait a minute. The force at this point is also going to be perpendicular. So in fact, the force is always going to be perpendicular to the velocity, right? It's going to move in a circle, right? Where the acceleration is always perpendicular to the velocity. And well then, hey, I remember what that is. I can solve that no problem. Because if I have circular motion, I have a constraint on my acceleration, it tells me that the acceleration should be the acceleration should be v squared over r, right? Equals qvb, right? And I dropped the k hat because the force has to always be perpendicular, right? So we're just looking at the magnitudes. So I can solve this for a radius, right? So this is going to kill off one of those, and you're left with mv over qb equals r. So it tells me basically how big of a radius or how big of some circular motion I'm gonna have. That depends on how fast I'm moving, or even its momentum, divided by the charge and divided by the magnetic field.